from the Geoscience Research Institute. In today's presentation, we will reflect about our planet, considering data acquired from scientific investigation and interfacing it with the biblical perspective. So, is the Earth special? That's the question in the title of this presentation. The opinions on this differ. For example, in their book, The Privileged Planet, Gonzalez and Richards build a case for our planet not only being exquisitely fit to support life, but also fit to give us the best view of the universe, as if Earth were designed both for life and scientific discovery. Now, in another influential book, Ward and Brownlee refrain from using the concept of design and adopt a naturalistic model of Earth history. However, they also come to the conclusion that the Earth is probably to be considered special or rare, as the title of their book suggests, because they suggest that complex life is less pervasive in the universe than is commonly assumed. Finally, we can also consider a different point of view. In his book on planetary climates, Andrew Ingersoll concludes the book with a statement that presents yet another view which minimizes Earth's uniqueness. Earth seems to be a typical planet orbiting a typical star with a typical collection of raw materials that constitute the building blocks of life. There is no reason to believe we are alone. So, in a certain sense, we see that there is this spread of understandings and postures when it comes to the Earth as a planet that can host life. Is this something unique and special or not? Well, from a scientific perspective, a new way to more directly investigate the question of how special the Earth is has opened in the relatively recent past with the discovery of exoplanets. Exoplanets are planets outside the solar system, and although their existence had been postulated earlier, their detection only occurred starting from the 1990s. And there are several ways of detecting exoplanets, but two are the most common. With this animation, we can begin to look at the first one, which is known as the radial velocity method. Now, this detection method is based on the fact that if a planet orbiting a star is quite massive, the center of mass of the rotational system will be a little off the star, meaning that the star too will be wobbling around the center of mass. So as we observe this rotating system from the Earth in a radial direction, the electromagnetic waves coming from the star will be compressed or dilated as the star moves closer and farther, respectively, in its wobbly motion. So this shift in wavelength illustrated at the bottom of the animation will be periodical, and from it one can estimate a minimum mass for the orbiting planet and also its distance from the star. Now, the second method, which we will see in this other animation, is the transit method. And this has been the most fruitful in the detection of exoplanets so far. And this is based on the fact that a planet transiting in front of a star will block some of the light that is received from an observer more or less aligned along the orbital plane. So that dip in luminosity, that drop that we see in the animation, will be greater if the planet's radius is larger, because it will block more light. Also, the dip in luminosity will be observed periodically as the planet keeps revolving around the star, allowing to calculate the duration of a full revolution and the distance of the planet from the star. Now, one implication for both these detection methods, as we will see from the next slides, is that they are biased towards finding larger planets orbiting close to the star. But with the application of these and other methods of detection, we can see how the number of confirmed exoplanets has increased over time. Here we have several plots in a time series, and on the plot we have the duration of the orbital period, or duration of the year in Earth days, on the x-axis, and the mass of the planet in Earth masses on the y-axis. So notice that the scale is logarithmic in both axes. We can see that in the early years, detections were based mostly on the radial velocity method and included only very massive planets. But then, as we move through the years, we see that especially with data from the transit method, the catalog expanded to include planets with masses less than 10% of the Earth's mass. And with our most recent count in 2021, in excess of 4,300 confirmed exoplanets. Now, the plot does not show yet a real overlap with our planet Earth in terms of orbital period and mass. You can see that the confirmed exoplanets with similar or smaller mass are closer to their star, and the planets with similar or greater orbital period are more massive than the Earth. However, it is expected that with improvements in detection methods, this field will continue to be populated. Now, the discovery of exoplanets has allowed us to ask questions, many new questions, like, for example, what kind of stars have planets? How many stars do actually have planets? And how common are Earth-sized planets? Or is there a relationship between planet type and size and the distance from the star? Or what fractions of exoplanets are in the habitable zone? All these questions are being investigated, but one thing is already clear. The number and diversity of exoplanets is much larger than number and diversity of planets that we have so far known in our solar system. And as the catalog grew, it included also some unexpected surprises. For example, the occurrence of gas giants similar to our Jupiter, but orbiting very close to their star. Most importantly, the exoplanet census illustrates that the possible set of planetary types and conditions is vast, so that Earth-like conditions are not a default in the universe. Let's then review together some of the parameters that astrobiologists, who are the scientists who study the conditions necessary to sustain life in the cosmos, let's review the parameters that they are considering as important for a planet to be a good place for complex organisms like us to live on. Here is an example of a definition. You can see that in this definition there are some key elements in the definition of habitability for a planet. First, we see the term mostly rock. So therefore the planet should be a terrestrial planet, not a gaseous one. Also a planet that can retain an atmosphere with certain specifications. Also a planet that has availability of energy sources with certain specifications. And then a planet where liquid water is present. And finally, a planet that can keep these sets of parameters stable over time. Now, this is just one definition of habitability, but no matter the specifications chosen to define habitability, it is clear that habitability is not a function of one single variable, but lies at the intersection of multiple factors that have to coexist. So it's a much smaller subset of all the possible physical chemical conditions present in the cosmos. So let's then review more in detail some of the commonly recognized parameters from planetary habitability. Now, although there are possible sources of energy that could be used to sustain life originating from the interior of a planet, the most important source of energy is light from the star around which a planet is orbiting. It is not only crucial as a source of energy for living organisms, for example on the Earth through the process of photosynthesis, but most crucially, it controls the possibility of having the right temperature for the availability of liquid water on the surface of the planet. Now, the temperature on the surface of a planet is a function of the distance of the planet from the star, among other parameters. So too close and it will be too hot for liquid water to be a stable phase. Now too far from the star and we will reach the frost line where water will turn into ice as the temperatures go below the freezing point. So this band or distance interval is called the Goldilocks zone or the habitable zone. And obviously, as you can see from the upper part of this illustration, the Earth is located within the habitable zone. Otherwise, we wouldn't have liquid water on its surface, right? Now, for a less massive star, like the one represented in the lower part of the figure, the habitable zone will be shifted closer to the star because of the smaller energy flux radiating from the star. Now, it turns out that not all stars are created equal. In our galaxy, stars less massive than the Sun, like M stars at the top of this illustration, these stars are more abundant than Sun-like G stars, which are represented at the bottom of the figure. So being less luminous, their habitable zone is located closer to the star. However, the M stars are also characterized by very high levels of emission of X-ray and ultraviolet radiation, actually up to hundreds times more intense radiation than what the Earth receives from the Sun. Now, these energy flares and bombardment of high-energy particles would affect the planets in the closely located habitable zone, making it difficult to preserve an atmosphere and also creating devastating effects for life. Moreover, at such close orbital range, a phenomenon which we will discuss later, which is called tidal locking, is also very likely to take place. And this would also decrease overall habitability. Therefore, even if there may be many planets in the habitable zone of a star, the kind of star and the type of radiation emitted are important parameters to consider for habitability. But why bothering so much about liquid water and even calling habitable the zone where temperatures are appropriate for the existence of liquid water on the surface of a planet? Well, we are all familiar with the fact that water is an important constituent of our bodies. What perhaps most of us do not realize is how intrinsic liquid water is to the life and metabolism of any living organism on Earth. As pointed out by Chaplin in an excellent review paper, liquid water is not a beat player in the theater of life. It's the headline act. Liquid water is essential for the folding, the structure, the stability, and the activity of proteins. It also plays a part in proton and in electron transfer reactions. And it plays a part in the structuring of DNA and in the recognition of specific DNA sequences by proteins. And it's also essential for the metabolic activity in the cell. So in other words, liquid water is essential for the biochemistry of life. No liquid water, no life. Let's now consider another important parameter for habitability, the atmosphere. Well, the atmosphere of a planet is important for life, not only for respiration, but also for temperature regulation by trapping some of the heat radiated from the planet. And it also controls climate. It provides a shield against some of the damaging solar radiation, and also it interacts with the hydrosphere and the lithosphere for the cycling of elements important for life. Now, when a planet is too small, its mass is too little to gravitationally maintain a stable, thick atmosphere. For example, in this image, we can see the thin, most likely ephemeral atmosphere of Pluto. However, even if a planet is massive enough to retain a thicker atmosphere, a thick atmosphere can also have negative consequences. Take, for example, Venus. Its thick atmosphere is rich in CO2, a greenhouse gas. What does that mean? Greenhouse means that gas is able to trap the heat irradiated from the planet. And so that leads to higher temperature. So if you raise the temperature, you increase the saturated vapor pressure of water, which is also a greenhouse gas. So what this will do will be to trigger a runaway greenhouse effect. And that is thought to have led to surface temperatures on Venus of over 450 degrees Celsius and complete loss of water from the surface of the planet. Now, why is it that on Earth we don't observe this runaway effect? Well, on Earth, CO2 is dissolved in the oceans and is also trapped in limestone rocks, preventing this runaway process. And so this is yet another example of a balanced interrelation between different components of a planet. In fact, do you know, it's thought that even the interior of the Earth could be linked to the preservation of its atmosphere. The core is where the Earth's magnetic field is generated, and that field helps deflect some of the particles that could erode some of our atmosphere. Well, as we have seen in the definition of a habitable planet, one important requirement for habitability is for the planet to be a terrestrial planet, to have a solid, rocky crust. And this is not just because it would be hard for us to walk suspended in the atmosphere of a gas giant like Jupiter. It's more important because of the availability of heavy elements on the planet's surface. These heavier elements, heavier than the lighter element like helium and hydrogen, these heavier elements are necessary for life. And note how in the solar system the terrestrial planets, which are highlighted by the rectangle, are also located in or near the habitable zone, closer to the sun. Now, the study of exoplanets has shown that this is not a given. It's not that terrestrial planets always have to be the ones that are in that particular location. Since there are other situations where instead of finding terrestrial planets closer to the star, we have gas giants at short distance from the star. Now, one should also note that the sun does not produce the heavy elements found in the Earth's crust. Standard models of planetary formation suggest that terrestrial planets form from the accretion of material out of a protoplanetary disk. So if this is indeed the way in which terrestrial planets form, it means that the protoplanetary disk must have the right initial composition to include the heavy elements. Therefore, not all stars will be orbited by terrestrial planets of the right composition. Furthermore, some have suggested that being a terrestrial planet may not be enough. It could be that the presence of active plate tectonics, as we observe on Earth, could be an additional requirement for habitability. Plate tectonics could be important for the maintenance of a magnetic field through interaction at the mantle and core boundary. It could also be important for cycling of the elements and the availability on the surface of chemicals important for life. And finally, through the process of crustal differentiation, plate tectonics could be responsible for the unique bimodal elevation profile of the Earth's crust. As you see in the diagram on the right, the Earth's crust has more buoyant continents with an average land elevation of about 800 meters and depressed oceanic basins with average depth of about 3.6 kilometers below sea level. So this difference is what allows for the existence of land masses above sea level. If we didn't have this crustal differentiation, then we would have probably a much more relatively flat surface, and therefore oceanic waters would cover the whole surface of the Earth without the possibility of having a dry landmass. One more element to consider for planetary habitability is the stability of orbital parameters. With this term, we mean things like the eccentricity of the orbit, the inclination of the axis of rotation of the planet, and the relationship between the speed of rotation and the speed of revolution, which are connected to familiar rhythms like the year, seasons, and the day. Now, it turns out that when compared with other exoplanets, the Earth and the planets of the solar system have unusually low orbital eccentricity. Their orbits are nearly circular. This implies more stability and less risk of disrupting gravitational interactions, but also this implies stable rates of solar radiation over the year. Imagine if the orbit of the Earth was more eccentric, more squeezed. What would that mean? It would mean that periodically we would get in and out, possibly even of the habitable zone. Now, in a recent paper, Bachmuller and Jorgensen conclude that low eccentricities are typical, are not an exception, they are typical of systems with multiple planets. So what makes our solar system special is the fact that it has 8 planets, and so, because of that, the orbits have low eccentricity. Their estimate is that only 1% of exoplanetary systems have 8 or more planets. Now, the axial tilt of the Earth is also another important factor that controls the seasonal cycle. The inclination of the axis of the Earth is about 23.5 degrees, and it allows a good distribution of insolation over the year cycle, even at high latitudes. Now, if we had lower or higher tilt, well, this could result in thermal extremes across latitudes or thermal extremes over the year. Moreover, the large mass of the Earth's satellite, the Moon, stabilizes the axial tilt over time. Without Moon, it is thought that the Earth's tilt could swing more widely, and that would carry dramatic consequences for its ability to retain an atmosphere. Finally, another orbital parameter that we often take for granted is the fact that on the Earth we experience the day and night cycle. Why is that? Well, this is because the period for a full rotation of the Earth, the day, is much shorter than the period for a full revolution, the year. However, it is possible for orbiting objects to slow down their rotation and attain a condition known as tidal locking, where their rotation and revolution periods are synchronous. And this is better illustrated by considering the Earth and Moon rotational system, like we can see in this little animation. Now, have you ever paid attention to the fact that we always see the same face of the Moon? It is not because the Moon does not rotate, but it is because the Moon rotates around its axis in about 29.5 days, which is the same time that it takes for the Moon to revolve around the Earth. Therefore, the Moon is in synchronous tidal locking with the Earth. Now, imagine a planet in tidal locking with its star. One hemisphere would always be exposed to the light of the star, and that would lead to reaching very high temperatures. And the other hemisphere would always be in darkness at freezing temperatures, with clear negative implications for habitability. So how important is this tidal locking phenomenon? Is it unlikely that exoplanets will be attaining this condition, or does it seem likely? Well, on a paper on tidal locking of habitable exoplanets, Barnes concludes, tidal locking is possible for most planets in the habitable zones of GKM dwarf stars. The process of tidal locking is a major factor in the evolution of most of the potentially habitable exoplanets to be discovered in the near future. So this is indeed a very important parameter. Now, starting from this overview of planetary habitability, let's now shift to the biblical perspective and what we encounter in the creation account in Genesis 1. The earth is presented with an initial state of being without organization and without life. Tohu, without form, vabohu, and void. And then what follows is God's action through the 6 days. And this action proceeds by organizing the spaces and filling them with life. What we have, therefore, is an extremely modern understanding of the connection between planetary organization and conditions as essential for life. In the 6 days creation, the forming is presented as an essential prerequisite, actually as integral to the filling of the earth. Now, the Genesis account is also very modern in presenting the essential parameters that God uses to organize the planet for life. We begin with light, the energy source. Liquid water is on the surface of the planet, and then we have the separation of the waters above, implying a connection between the atmosphere and the hydrosphere. Then we have the appearance of dry land, which signifies the rocky nature of this planet, but also potentially a process of crustal differentiation. And then finally, on day 4, the establishment of stable cycles, years, seasons, and days, which are all related to orbital parameters. Now, although the biblical perspective and scientific insight integrate very well when it comes to planetary habitability, we also need to acknowledge an important area of tension, the question of process. First of all, scientific models of planetary formation and Earth's planetary evolution are based on a long chronology of millions to even billions of years. Secondly, these mechanistic models rely on a naturalistic approach that denies any divine intervention. Let me just interject at this point that even if we had a perfectly naturalistic model for creating a habitable planet, that does not ensure that there will be life on it. There is no naturalistic model that can presently account for the emergence of life from inanimate matter. So, in other words, planetary habitability is necessary but is not sufficient for life. Now, this clarification aside, how do I deal with this tension between the standard models of planetary formation and evolution and the biblical account of origins? When it comes to the question of time, the passive gap theory, which basically suggests that the universe and the planet Earth without life on it are much older than creation week, this model could alleviate some tension. But the recent creation week still includes significant planetary organization that would generally be accommodated in standard models over a long time. So the tension remains. And what about facing the naturalistic nature of this model? Well, for me, when I face this naturalistic alternative or this naturalistic approach, the Word of God remains my anchor. I confess my ignorance about the actual process that God used for planetary organization, if through accelerated process or if by fiat or on a pre-existing earth, but I trust that He did it and in a recent creation week. So what do we do then with the amazingly insightful and sophisticated mechanistic models of planetary accretion and evolution? Do we throw them out of the window? No, not at all. My attitude is to keep learning and exploring. There is much value in knowing and hypothesizing. The synthesis, when it is not there, will come one day. Moreover, the practice of science teaches you a certain humbleness and gives us a better acquaintance with nature and its facts that we would not otherwise gain. So, we are back then to our original opening question. Is the Earth special? Well, perhaps it is too early to tell. Recently, Kunimoto and Matthews have published probabilistic estimates suggesting that the probability for a G-star like the Sun to have a rocky planet of a size similar to the Earth's and orbiting within the habitable zone is less than 18%, which would translate into about less than 6 billion possible exoplanets that meet these requirements within the Milky Way galaxy. However, as we have seen, there is much more to habitability than just radius, distance from the star, and type of star. In any case, maybe there are many Earths, or maybe there is just one. But what counts is that we live in a universe where the Earth, our Earth, is habitable and there is life on it. That is the most amazing fact, confirmed by science. You and I are that miracle. Scientific insight helps us appreciate the complexity of life and how among a myriad of possible combinations of different parameters, the Earth is a marvelously suitable space for us to live our lives. The Bible cuts through the noise and reveals in straightforward terms why this is so. It is so because God wanted it and did it. The Lord created the heavens. He fashioned and made the earth. He founded it. He did not create it to be empty, but formed it to be inhabited. In considering the miracle of our existence today on planet Earth, you and I face a choice. God has made a claim of ownership. We can reject it or embrace it. My invitation? Embrace it. Embrace it because it's the truth, and the truth will set you free.